Kinjal Shah from Facebook.
Hi.
Hi. When you're ready, take it away.
Yep. Cool. Okay, so hello everyone. My name is Kinjal. I'm from Facebook's probability group, and I'll be presenting our paper on a new probabilistic programming language called Bean Machine. So here's a preview of what we'll be covering in the talk. We'll begin with a brief overview of both just PPLs in general, as well as our new PPL, Bean Machine. Then we will dive deeper into the modeling aspects of our language, that is how users can write models in Bean Machine. Then we'll go over how we do inference. And finally, we will go over the programmable inference techniques in Bean Machine, where users can write custom inference that is best suited for their problem without having to handwrite the entire inference. So let's begin by motivating the need for a PPL. So generative models are valuable in domains where we have some knowledge of the problem, but small amount of data. And often, as part of developing a new generative model, statisticians manually handcode the inference algorithms. However, this requires the modeler to know how probabilistic inference works, and this becomes infeasible for more advanced inference algorithms. It also leads to unnecessary duplication as we write up the same inference algorithms repeatedly for different models. However, with a PPL, users can just specify the models and the PPL will automatically perform inference on it. So this brings us to the definition of a PPL. PPLs provide a formal language for expressing statistical models and a general purpose inference engine for performing probabilistic inference. At Facebook, we use PPLs at scale for problems in ads, experimentation, and integrity. So here's an example model from the integrity space. We call this the annotation model. Let's say we have a group of news articles and we're interested to find what percentage of them are fake. We will send these articles out to labelers, and each labeler will classify each article as being fake or real. And our goal is to account for individual labeler biases and determine the true class of each article. At Facebook, we model this problem using a directed graphical model, as shown on the right, and use a PPL to perform inference. Okay, so what is the problem? The issue is that PPLs still lag behind handwritten inference in performance and level of customization. So the question is, can we do better? And we believe we can. We present a new declarative universal PPL, Bean Machine, which is built on top of PyTorch, which offers 3 programmable inference techniques: compositional inference, block inference, and custom proposers. And these techniques bring us closer to the level of customization that handwritten inference gives us. So folks are always intrigued by the name Bean Machine when we introduce our language. So a quick note about the name. We have named this after the device Bean Machine, or the Galton board. For those who are unfamiliar, this device has a bunch of pegs, and we can drop beans from the top, and the beans ultimately fall into a normal distribution. Our team likes to think of this as the world's first PPL, so the name was motivated from there. Anyway, let's get into modeling in Bean Machine. So there are 2 main classes of model representations used among PPLs. The first is imperative, which is used by most of the PPLs. We have Pyro, Gen, Stan, Church, Turing. Then there's declarative, which is used by Blog and Bean Machine. In a declarative syntax, variables are defined with a separate code block. The model itself does not provide any order in which to draw samples from. And the dependency among variables, which is the underlying directed graph, is explicit. While in an imperative syntax, all variables are defined in one main code block. The model provides an order in which to draw samples from, and the directed acyclic graph is implicit. So to understand these better, let's walk through an example together. Let's consider a hidden Markov model. Here's a quick recap of HMM. We have some parameters, mu and sigma, for each hidden state. We have theta, which represents the probability of transitioning between states. We have our x's, which are our hidden states. Finally, we have our emissions y, which are normally distributed, and the parameters depend on the latent hidden state. We observe everything except the x's and the length of our sequences n. On the right, we can see the corresponding graph. And we see that our observations y depend on the hidden state, as well as the mu's and sigmas, and the hidden state depends on theta. In Bean Machine, we will write the model as specified here. So each variable is a function annotated with the @random variable decorator. Each function returns the conditional probability distribution of each variable, and the arguments to these functions are subscripts of the variables. So for example, we have mu of k is a function that returns a normal distribution, theta of k is a function returning the Dirichlet distribution, and so on. It's worth pointing out the nice similarities between the mathematical notation and the modeling representation. In contrast, in the imperative version, we'll write the model as follows. If we have k hidden states, we loop over k and sample mu sigma theta for each state. We then loop over all n, which is the sequence length, sample the hidden state, and then pass in our observations to the y's. Note that we provided an order in which to sample variables. For example, sigma of each state was sampled after its mu. We had to know n when writing up the model, and we had to also pass in strings to identify variables. Okay, so the key takeaway so far is that in Bean Machine, we write models in a declarative style. Now let's talk about inference in Bean Machine. So to perform inference, Bean Machine uses Markov chain Monte Carlo, which represents the inferred distribution as a set of samples. Specifically, we use single site Metropolis Hastings, which we would refer to as SSMH from now on. In SSMH, we propose and accept project a new value for each variable one at a time using the Metropolis Hastings rule. The key is that because the dependency between variables is explicit, when a variable is updated, we just need to update the random variables in its Markov blanket. Therefore, the runtime complexity of an update is proportional to the size of a variable's Markov blanket. And this makes second-order gradient-based proposal methods like Newtonian Monte Carlo tractable. So let's go through this with an example using the HMM model. So just to recap, we observe mu's, sigmas, thetas, y's, and we want to infer the x's, which are our latent hidden states. To run SSMH, we iterate over the unobserved random variables in a random order. We then perform an MH update, which starts with proposing a new value. For example, let's say x1, which is the hidden state at time step 1, was 0, but we propose 1. We then update the distribution of its children to reflect the new value of x1. The immediate children of x1 are y1 and x2. And we update the children's parents. So for example, y1 originally came from normal of mu 0, sigma 0, but now it would come from normal of mu 1, sigma 1. Now we accept or reject all of these changes together using the Metropolis Hastings rule. Because Bean Machine has the explicit dependency structure, the runtime of inference per variable is always proportional to the size of its Markov blanket. In HMM, the Markov blanket is constant, and so we achieve a linear runtime complexity with respect to the length of the HMM. In comparison, it is harder to extract the dependency in an imperative setting, and they often need to resample the rest of the trace. In this case, the runtime per variable is linear with a total quadratic complexity. So we can see this in this graph. As the length of HMM increases, Bean Machine is able to scale linearly, while Gen, an imperative language, shows a quadratic increase. Here we showcase how inference is called in Bean Machine. We instantiate the inference algorithm we're using. In this case, because we have discrete variables, we're using a uniform sampler. We create a list of random variables that we wish to query. We create a dictionary of observations, binding random variables to observations. We pass in queries and observations, and Bean Machine creates the graph and automatically performs inference. Okay, so the key takeaway so far in terms of the underlying inference techniques is that we perform single-site moves and exploit the underlying model structure to do so in an efficient and scalable way. Okay, so the declarative paradigm allows us to make single-site moves, which in turn paved the path for us to offer a series of programmable inference techniques with ease. And this is really the key contribution here. So we'll talk about 3 different types of programmable inference. We'll cover composition, blocking, and custom proposers. So let's start with composition. Because we use SSMH and propose a value for random variables individually, we can use different proposers for different variables. A consequence of this is that, unlike in some other PPLs, Bean Machine does not need to integrate out discrete variables. Here we have the annotation model again, which has a mix of continuous and discrete variables. For example, Z is the true category of each article, that is, whether an article is fake or real and is discrete, whereas the accuracy of labelers, which is theta, is continuous. In Bean Machine, we can specify that we want our continuous variables to use the gradient-based proposer, Newtonian Monte Carlo, which is a second-order gradient-based method, and the discrete variables to use the discrete proposer, Uniform Sampler. Here we compare performance of Stan versus Bean Machine on this model. We plot the predictive log likelihood on held-out test data and notice that both Stan and Bean Machine converge to the same value, which is a good sign. However, we see that Bean Machine achieves a slightly higher effective sample size compared to Stan by doing compositional inference. Okay, so the next inference technique we support is blocking. Because SSMH proposes values for each variable individually, it may not be effective when we have highly correlated variables. Blocking allows us to specify variables we would like to update together. So let's revisit the HMM example. This is the same model as before, but now we only observe the y's and we want to infer the hidden states as well as properties of the hidden states. So let's say x1 was 0, but we propose 1. When we propose this new value for x1, it'll change y1's parents from mu0 and sigma0 to mu1 and sigma1. Now, although the dependencies have been updated, we haven't really updated the values of mu1 and sigma1. So when we're computing the likelihood of this new world, we'll have a term, probability of y1 given mu1 and sigma1, which is likely to have very low probability. The old values of mu1 and sigma1 are not explaining y1, and so this updated world has a low chance of acceptance. Block inference allows us to group x's, mu's, and sigmas to be updated together. So when we propose a new value for x, we also update the values for mu and sigma that are affected by this change. And that's the key here. We're not going to update all the mu's and sigmas, but just the ones that are going to be affected by the change in the particular value of x.
Hi, Kinjal. You have about 5 minutes.
Okay, thank you. So the first step is the same. We propose a new value, x prime for x, and we update the random variables in its Markov blanket. Then new values are sequentially proposed for the affected mu and sigma. To do this, we track the Markov blanket of both the old and the new value now. So for each mu in this Markov blanket, we will propose a new value. We will update the Markov blanket of that new value. We'll repeat this for mu1 as well as sigma0 and sigma1. We'll then accept or reject all these changes together. So we've changed values for x1, mu0, mu1, sigma0, and sigma1. Note that the value of mu2 has not been updated because it is not within the Markov blankets of whatever was being changed. Here you can see that as the number of hidden states increases, with block inference, effective sample size stays consistent, whereas without block inference, we notice a significant drop in effective sample size. The syntax for block is also straightforward. We just need one additional line, which is add sequential proposer, to specify the variables we want to update together. The inference will only update the variables within the markup blanket, keeping the algorithm efficient. Okay, so the third type of programmable inference that Bean Machine supports is custom proposers, which allows users to easily incorporate domain knowledge to inference. And we showcase this using a simplified model from seismology. In this model, a seismic event takes place on the surface of the Earth, and there are stations around the Earth which have some probability of detecting the event based on the magnitude of the event, its location, etc. If the station does detect the event, it will record some detection attributes, such as the time and speed of the waves. And the inference problem is, if we only have the detection attributes, can we locate where the true seismic event took place? So there's a lot of domain knowledge to invert the detection attributes to find the most likely event attributes, that is, where the event took place. So here, the green station may predict the green star, the blue station, the blue star, and so on. These predictions are noisy. However, we hope that they're a good indication of where the true event might be. So our idea for a custom proposer is to use a Gaussian mixture model proposer around these inverted attributes. So writing a custom proposer only requires two methods, propose and post-process. In propose, we first read the detection attributes, then use our domain knowledge to invert these attributes. We then construct a Gaussian mixture model around these predictions, and we return a sample from the Gaussian mixture model, as well as the probability of our sample. In post-process, we return the probability of the GMM proposing our current value. Here are two trace plots of the samples from two different events. On the left, you can see that the custom proposer with the red dots is able to find the true attributes, denoted with an X, much more quickly than the other proposers, but notice that all proposers find the true location. However, on the right, we notice that HMC with the green dots was never able to find the true attributes, whereas custom proposer was. When we looked at the true posterior, we noticed that it was multimodal. Our custom proposer was able to find the correct mode marked with an X, while HMC was stuck in the other mode, which had a slightly lower probability. And the reason we were able to do this is because we used domain knowledge to guide inference.
You're there. Great. Yes, I was going to ask if you could wrap up.
Okay, sorry. Yeah, so in summary, Bean Machine is a universal declarative PPL with syntax that mirrors mathematical notation. We perform single-site moves over individual random variables, which allows us to support 3 programmable inference techniques: blocking, where we update highly correlated variables together; composition, where each variable can specify its own proposer; and custom proposers, where users can easily incorporate domain knowledge to inference. And last thing before I conclude is, while developing Bean Machine, we thought it could be useful to have a benchmarking framework to compare what we're building with other PPLs. So we built one in-house called PPL Bench, and we used it to generate all our graphs in the paper, and we open sourced it a couple days ago. So do check it out. And with that, I'm happy to take any questions.
All right, let's all thank Kinjal in chat. A little bit short on time, so I'm going to take only one of the questions that there are in Q&A, and I'm going to ask other question askers to follow up offline. So the question I'll ask is, could you say something about use cases for Bean Machine internally at Facebook? Like, are you kind of close to deploying this? Are you deploying this? And if you're not yet deploying it, what would be kind of needed in order to really make this usable for internal purposes?
Mm-hmm. Yeah, so in fact, we have Bean Machine deployed in one of the use cases at Facebook in the experimentation space, and we are actively working to also deploy this on a problem in integrity. So Bean Machine is at a stage where it's scalable, it's modular, it's expressive, so it's easy to write models in, and it also perform scalable inference. So we are using this at scale at Facebook for our internal use cases.
Let's all thank Kinjal again in chat. We're going to move on.